like that. So this we will call as at this point, it seems that the CT entered into the saturation. This point we will call as its flow, it's having some knee point. So this is the knee point voltage. It's a knee shape, right? So it's a knee point voltage. So what is the concept behind this? Generally, the EMF induced in the CT secondary, this is the equation we already know, which is 4.45 flux and T into 2. So T2 in the sense number of turns that you know, right? Number of turns of the secondary winding. The flux in the core is generally produced by the excitation current IE. Excitation current IE. So here we are having a non-linear relationship between the excitation current and the magnetizing flux. After certain value of that excitation current, flux will not further increase so rapidly as you can see increase in the excitation current. What we discussed before, because after some primary current, the flux is entered, the flux cannot change, means it reaches its to maximum flux density, the flux cannot change, so it will not impact the flow in the secondary side of the CT. So the most of the current you can see in the primary is building up for the excitation current. What we discussed before. This may give results to the nonlinear relation curve of BH curve. So if you see here also in this equation, the secondary voltage is directly proportional to the flux. Is directly proportional to the flux. So from here curve also you can see that there is some linear relationship between the voltage and excitation current up to some point from A to K. The A we will call as an ankle point and K is the knee point voltage. Beyond K, the primary current is increased further. The flux is reached to its maximum current density. No change in flux, no current in the secondary winding of the CT. So whole the current which is on the primary is going in the knee point, see in the excitation current. So the excitation current is building up here, is increasing with just small change in the secondary winding of the current. Why I need to concentrate on this knee point voltage here? The same phenomena we have seen in the before protection 5P10 class CTs also. The same thing is applicable in the metering also. Why we are much focusing on this knee point voltage? Why here I am trying to figure out the knee point voltage. So to know this, we need to know the operation of the differential protection first. Generally, the differential protection. So this is the different transformer. These are the two CTs which are placed on either side of the transformer. If any fault occurred in the transformer, then the operation, then the relay will operate. This is the principle of differential protection. And if any fault occurred outside of this zone, means after this CT or after this CT, this relay should not operate because the fault is not inside the transformer, it is outside. So this is my objective or the aim of my differential protection. So in these differential protections or area restricted earth fault protections, accuracy class and ALF of the CT, ALF like we discussed, the accuracy class like metering class CTs, or ALF the protection class CTs, may not ensure the reliability of the operation, because I stated before the differential protection and RF relay should not be operated for the faults occur outside of the transformer. Suppose when a fault occurs outside of the differential protection zone, the fault current will flow through these CTs, on both sides of this transformer. The both low voltage CT, I mean the 33 kV CT as well as the 220 kV CTs, have the magnetizing characteristics beyond the knee point. Both are having definitely the magnetizing characteristics. All the CTs having the magnetizing characteristics. Now, beyond the knee point, for a slight increase in the secondary voltage, a large increase in the excitation current is required. So, after this knee point voltage, excitation current of both current transformers will be extremely high, which may cause the mismatch of between the secondary current of my LV and HV, and this leads to the mal-operation of my differential protection. Got my point? What I'm saying, these both is having different magnitudes, magnetizing characteristics. When it's reaching to its knee point voltage, with a small increase in the knee point voltage, you can see there is a much increase in the excitation current. So this may leads to the mismatch on the secondary side of the currents, and the relay may operate, which is a mal operation. So what I have to do? I have to ensure that the knee point voltage of CT and magnetizing characteristics of CT of the both sides of the transformer should be same. If they differ, there must be a mismatch in the excitation current and causes the unbalance between currents flowing in the secondary CT, and it will trip my transformer. So I have to select the CTs on either side of the transformer should have the knee point voltage same and having the both same magnetizing characteristics. So to determine this, the CT should be designed with respect to the knee point voltage and excitation current at half of the knee point voltage. That class of CTs we will call it as a PS class, special protection class CTs. So we are having a formula for this knee point voltage. This knee point voltage formula is again depends upon the manufacturer dependent, means the relay, which relay you are using for differential protection. So from the relay catalogs, we will get this formula, and from that we are calculating this knee point voltage. Generally, the knee point voltage, it depends upon the X by R ratio. One way of calculating the knee point voltage is X by R ratio. Other one, in some articles, they will show you the calculation with respect to the dimension factor of the CT. It was recommended to use this dimension factor of the CT to calculate the knee point voltage. But anyway, we not much go in deep on this. I will share you some related stuff regarding this, so you can find out the way of calculation on this. But mostly we are calculating this knee point voltage based on the relay what you are using here for the differential protection. So this is about the knee point voltage and the PS class series. Fine, team? Clear?
Sir, but the relay coordination is done after the
Relay coordination in the differential protection will not be done. It's a unit protection.
zero prediction.
Yeah. Fine, team? Clear, everyone, on this? Yeah. So now let's see the calculation of this team. Team, able to see this calculation, team? Hello? Yeah, fine. So this is an 8.1. Let's first talk about the metering class 1, and then we will talk this. Let's see this. So this is the metering class CT, team. I am calculating. So this CT is connected to MFF metering and some other relays. One is a PAC 3220, so maybe a BCPU. Light is the one. Connected instruments. And this is my power, and I'm just 132 kV switchgear. I'm calculating the current, which is the rated current, which is 486. So for time being, this is before for some other classes I changed this. That's why there is some discrepancy here. But just see the flow. So I am selecting a 1200 bar 1 amp CT for this application. So as I said, I am considering 0.2s class CT here for the metering. 0.2s is the accuracy class of CT. So this is the CT accuracy class finisher. And the next one, what I told, we have to calculate the burden. So I'm calculating the burden from the catalogs. I found that Siemens is having a burden of 0.1. Elite is this. And the total burden, total connected burden for the CT is 0.25 and 25 VA. And this is the from the relays. And what is the relay? Cable is there, right? That cable, I am calculating the resistance, which is a 4 square mm cable and having a resistance of 5.52 ohm per kilometer from the catalogs, again from the Polycap catalog. And the length I laid for that cable is 100 meters. So I calculated that and I found that is a 1.104 VA. So I'm adding this with the 0.3. So total, my burden is 1.35 only. What is my burden of the CT? 1.35. But I selected the CT burden as 10 VA because taking some margin, maybe tomorrow some other, if I require to connect any other relays. So I'm taking a margin. So I take as a 10 VA. But for the meterings, what I told, I have to secure the meters which are connected on the secondary side of the CT. So the ISF rated is 5. ISF is 5. Now let's see what is the actual burden 1.354. What is my rated burden 10 VA. Now this is the formula ISF. What is now? This is the rated ISF. Now I am calculating the actual ISF, which is ISF rated into which is the rated burden plus RCT into NIA square, means the actual burden plus again this is the secondary side of the CT's burden. So now my actual ISF is not 5. My actual ISF is 14.93. If it is a 14.93, what it seems, even though my rated current, my primary current is 12 times of its rated current also, my CT will not enter into the saturation. So there is a chance of flow of 14.93 amps in the secondary. Now I have to check whether my equipments like the Siemens 1 and Elite are capable to carry 14 amps or not. In the catalog, it was shown that this one can carry 100 amps for 1 second. This is 20 amps for 1 second. Mine is only 14. So more than this, 20 amps. So the ISF at actual button is less than the overcurrent capability of the unconnected instruments. So ISF for this one is safe. You can select up to 10 VA. Suppose I am selecting 15 VA button. Then see 20. You cannot, because this equipment will damage. So it was limited to 10 only. If you go for 5 VA button, see 9. If you go for 2 VA button, 5 only. Very good. But again, for a future expansion, I'm considering and taking it at 10 VA button. So this is and my conclusion is this. 10 VA button, ISFS rated button is to be 5. Rated button in the sense, this. At 10, it should be 5. At actual, it is 14.9, which is less than the overcurrent capability that I already checked. So I can find that, I can conclude that this is the CT I required for my metering application. Clear, team? Now, go to the protection. Let's see the protection. Okay, let's see the PS class CTs. This I am connecting for busbar protection, which is a unit protection. Again, I am calculating the CT rated current 1200 by 1 amp. So as per the Siemens relay catalog, the CT knee point voltage is this. So I am calculating this with respect to this formula. That's it. And I am calculating the button. That's it. This is the only thing required for